Good day everyone, welcome back to OneCodeCamp channel. Today, we'll be creating a Web3 lottery game called Boxing Bonanza. Join us as we explore the mechanics of creating a decentralized application where players can place predictions on virtual boxing matches. With Boxing Bonanza, we'll be crafting a transparent and secure lottery game that harnesses the power of Ethereum blockchain. By utilizing smart contracts and leveraging Chainlink's advanced features, we'll guarantee the fairness, randomness, and trustworthiness in our gaming experience. Let's begin by implementing our smart contract using Remix IDE. Since Remix IDE is a web-based application, you can open it in your browser by visiting the link provided in the video description. This IDE offers several advantages for smart contract development. It is user-friendly and eliminates the need for local installations. In this application, there are several useful features that we can use in our smart contract development. First, the File Explorer. It allows you to navigate through your project's directory structure, create new files, and manage the existing files. The Search File tab provides a search functionality that allows you to quickly find specific files within your project. We also have a Compiler tab to compile and run our code for our smart contracts. And lastly, we have the Deploy and Run Transactions tab. It allows you to deploy your smart contracts and interact with them. To begin working in the Remix IDE, click on the plus icon located at the top corner of the File Explorer panel. This will open a prompt to create a new workspace. To get a clean slate state of our components, let's click the blank template. Type any name that you prefer. After that, click the OK button. Now to create your smart contract, choose the Create New File option from the context menu and name your project. Make sure to give it a name with a .sol extension. We'll begin by specifying the license identifier and the compiler version. This ensures that our code is protected and compatible with the required compiler. In the first line, you can see that we have added the SPDX license identifier to indicate that our code is unlicensed. This means that others may use, modify, or distribute your code without explicit permission from you. The second line is a version pragma statement that specifies the version of Solidity compiler that should be used to compile the contract. The next thing we'll do is to import two external Solidity libraries that will be important for our project. To begin with, let's proceed to the Chainlink documentation website, where we can access the documentation for the first library that we'll be using. The links to these libraries will be available in the video description below. Scroll down the website and locate the BRF-V2 section. There are two methods to use Chainlink, the subscription method and the direct funding method. For now, let's proceed with the direct funding method. Click the Get a Random Number and scroll down again. You'll see the smart contract sample. Copy this line where the BRF proper consumer base.sol is being imported. Paste it in the Remix IDE. This contract provides functionality for consuming random numbers generated by Chainlink's verifiable random function, or BRF. By leveraging Chainlink's BRF, we can introduce randomness into our game, ensuring fair and unpredictable outcomes. The next library that we need to import is the ERC20. Let's proceed to the OpenZeppelin documentation website. From this webpage, click Contracts, scroll down a little, and from the sample code, click this line of code. Let's paste it. This interface defines the standard functions and events that an ERC20 token contract should implement. ERC20 tokens are commonly used in Ethereum projects for various purposes, such as in-game currencies, rewards, and more. By importing these libraries, we gain access to pre-built functionality and standardized interfaces, saving us time and effort in developing these features from scratch. Now let's dive into the heart of our project, the Boxing Bonanza smart contract. Let's start by typing the keyword contract. It will then be followed by the name of the smart contract. Let's say that I want to name my smart contract Boxing Bonanza. Inside this contract, we'll define various functions, events, and data structures to facilitate gameplay and maintain game state. But before we add anything inside our smart contract, I would like to add one more thing here in line number 7. Let us add the keyword is, followed by the BRF B2 wrapper consumer base. What we did here is we inherit the BRF B2 wrapper consumer base. By inheriting from the BRF B2 wrapper consumer base contract, we gain access to various functions and variables that facilitate the integration with Chainlink's BRF. Now you'll notice that it is throwing us some errors because we have some lines with red line. You can ignore that for now. It only means that the library that we have imported requires necessary function in order for it to work. We will add them later on. Let's add the first function that we need, and that is the start game. This is where the actual game prediction process will take place. Let us also declare this function as external and payable. The function is made payable because players are required to pay a certain fee when they participate and make game predictions. Later on, we'll also make this function return a request ID. So let's add returns uint56. Above this function, let's add an enum. We can use an enum to define the available choices for the players when placing predictions, which include red, draw, and blue. This will be passed down in our function as parameter with the value of red, draw, and blue, and place it in the argument choice. The next thing we'll do is we'll add two events in our smart contract. We will add the game ID and game result events to track the game's ID and the result of each player. The first event is emitted when the game starts, indicating the generated game ID or request ID. The second event that we need is the game result event. It will be triggered when the game ends, providing the player's address, the game ID, and the boolean indicating whether the player has won or not. First, let's type address player. Next, uint56, game ID. And lastly, we have the bool did win. When the game ends, this event will be emitted, telling our front end the result of our matches. Before proceeding with the functions, let's define the required data types. Let's start with a struct. A struct is a data type that allows you to group together different variables with different data types under a single name. It allows you to create custom data structures that can hold related data elements. Let's name our struct game status. Inside this struct, let's add uint56 piece. This is the payment required in order for us to request a random number using Chainlink BRF. After that, let's add uint56 random word. This is randomly generated number that will determine the game's outcome. Let's add address player. This variable stores the address of the player participating in the game. We also need a boolean did win, with a value that indicates whether the player won the game or not. Since we will request a random number in chaining BRF, to determine if our request is already fulfilled, let's add a boolean fulfilled. The next thing that we'll add is a field that represents the player's choice or prediction in the game. This could be an enum with the value of red, draw, and blue as defined as earlier. Next is the entry fee, which will store the amount of value required to participate in the game. Finally, the last data that we need is winning result. It can be used to compare with the player's choice to determine if they have won the game or not. Now let's add a mapping. A mapping is a data structure that allows you to associate values with unique keys. This mapping will be used to store the status or information of each game, where the game ID serves as the key and the game status represents the corresponding information of the game. Additionally, let's add another struct. To track and store win statistics, we will create a struct named WinStats. This struct will consist of 3 variables: red wins, draw wins, and blue wins. These variables will keep a record of the number of wins for the respective outcomes in our game. We will also declare a public variable WinStats of type WinStats. By making it public, we will allow external contracts and users to access and read win statistics stored in the WinStats variable. With this implementation, we can easily track and monitor the win statistics of the game. Next, we will add the constants required for the chaining PRF, P of the callback gas limit, the num words, and request confirmations. First, we will set the callback gas limit constant to specify the maximum amount of gas that will be allocated for the callback function. By limiting the gas usage, we can ensure that the callback function does not consume excessive gas, which could lead to out-of-gas errors or inefficient gas usage. In this case, we will set the gas limit to 250,000 Wei, indicating that the callback function should not exceed this gas limit during execution. To determine the number of random words requested from the chaining PRF, we will define the num words constant. The num words constant specifies the quantity of random words we want to retrieve from the BRF. In this case, we will set the num words to 1, indicating that we are requesting a single random word from the chainlink BRF. To establish the number of required confirmations for the chainlink BRF request, we will introduce the request confirmations constant. This constant determines the minimum number of confirmations we expect to receive for the BRF request to be considered valid. We will set request confirmations to 3, indicating that we require a minimum of 3 confirmations for the chainlink BRF request. The next thing we'll do is we will define 2 constant addresses that are needed for our smart contract. First, we have the link address. We can keep the link address constant empty for now, and I will provide you with the guidance on how to obtain the address shortly. The next constant that we need is BRF wrapper. The link address represents the address of the Chainlink token contract, while the BRF wrapper represents the address of the Chainlink BRF wrapper contract used for accessing Chainlink's random number generation. To obtain the address values for the link address and the BRF wrapper variables, let's navigate again to the documentation website of Chainlink. From the Chainlink website, scroll down and find the section BRF V2. Then click the direct funding method. Navigate through the sidebar and then click Supported Networks. From this section, we can explore the various networks supported by Chainlink. Let's continue scrolling down until we find the section related to Polygon Mumbai testnet. From this section, we can now copy the address of link token and BRF address. Let's go back to the Remix IDE and paste this address in the respective variables. Now that we are already done in setting up the data structures that we need, we can now add a constructor. It is marked payable, allowing the constructor to receive Ether along with the contract deployment transaction. We will also ensure that the base contract BRF B2 wrapper consumer base is properly initialized with the provided link and BRF wrapper address. We do that by passing the link address and BRF wrapper values as arguments to the constructor of the base contract. This initializes the base contract with the provided values. We can now go back to the start game function. The first step in this function is to request a random number using the request randomness function. We assign the return value to the request ID variable. This line is used to initiate a request for random numbers using Chainlink's BRF. And it takes 3 parameters: callback gas limit, request confirmations, and num words. We will then store initial gain details in matches mapping. Let's start by passing the request ID as parameter. What we did is we access the matches mapping and assign the game details to the corresponding request ID. We will then set the piece by calling the calculate request price function of the BRF B2 wrapper contract. Passing down the callback gas limit as parameter, this function calculates the required fee for the game request. Let me just fix this one. This should be a comma. After that, let's set the initial value for the random word as 0, as it will be updated later with the actual random word generated. Let's set the player value as the address of the player who initiated the game request, or the message that sender. Set the initial value of did win as false, indicating that the game result is yet to be determined. Similarly, we set the initial value of fulfilled to false, which signifies that the game request has not yet been completed. Let us set the choice value as the player's chosen option. We will also set the NVP as the amount of Ether sent by the player, or the message that value. Lastly, set the initial value of winning result as 0, indicating that the winning result is yet to be determined. After storing the game details in the matches mapping, we will emit the game ID event by passing the request ID as parameter. This event notifies the listeners for external applications about the newly created game and provides them with a responding request ID for reference. To complete the start game function, we need to add a return statement to return the request ID value after emitting the game ID event. This allows the caller of the function to retrieve the request ID for further reference or tracking. Now that we are done creating the start game function, we will now create the fulfill random words function. The fulfill random words function is responsible for processing the generated random numbers and updating the corresponding match status based on the outcome. The function takes two parameters, request ID, which represents the unique identifier for the random number request, and random words, which is an array containing the generated random words. Inside this function, the first step is to check if the requested gain exists by verifying the corresponding P is greater than 0. If the request is not found, an error message is thrown. The fulfill random words function is an internal function that is overridden from the BRF B2 wrapper consumer-based contract. Inside this function, the first step is to check if the requested gain exists by verifying the corresponding P is greater than 0. If the request is not found, an error message is thrown. The game status for the specified request is updated to mark it as fulfilled. The function assigns the first element of random words array to the random word property in the game status, representing the generated random number. The next step is to calculate the winning result by taking the modulo of the random number with 3. This ensures that the result falls within the range of 0 to 2. 0 being the red, 1 is draw, while 2 is blue. The result is then assigned to the game status winning result. Our next step involves creating a conditional statement. We will compare the player's choice with the winning result. If they match, indicating a correct prediction, the player is marked as winner, and the winning amount is transferred to the player's address. The winning amount is calculated as 3 times the entry P. Let us set the boolean did with into true. And let's use the payable keyword to enable transferring funds to the player's address. The transfer function is then called to transfer the winnings, which is calculated by multiplying the entry fee. The function also emits the game result event, providing information about the player, request ID, and whether they won or lost the game. I forgot one semicolon here. Lastly, inside this function, we will also update the stack of win stats based on the winning result. If the result is 0, it increments the red wins counter. If the result is 1, it increments the draw wins counter. And if the result is 2, it increments the blue wins counter. This allows tracking the win statistics for different outcomes. We're nearing completion, but we have one more task remaining: adding getter function. Getter functions are essential as they enable us to retrieve specific data from the smart contract. They provide convenient way to access information stored within the contract. Let's start with getStatus function. By providing this function, other contracts or external systems can query the status of results of a specific match by calling this function with appropriate request ID. Next, we have the getWinStats function. By invoking this function, you can retrieve the current values of red wins, draw wins, and blue wins stored in the WinStats track. To do this, we will simply return the WinStats variable. Given that our smart contract utilizes link token as payment for requesting random numbers from the BRF, we will now create a function to fetch the balance of link tokens. This function is called getLinkBalance. It will enable us to obtain the current balance of links tokens stored within the smart contract. Let's also create a function called getItBalance. It will enable us to retrieve the balance of Ether, or in this case Matic, that is stored in the smart contract. In addition to that, we'll also include withdraw functions. This will enable us to withdraw either link or Ether from the smart contract. Let's call it withdraw link function. This function allows us to withdraw a specified amount of link from the smart contract. For the other function, let's call it withdrawIt function. The last function that we will include is receive function. This is a special function in Solidity that allows the contract to receive Ether when it is sent to the contract without any specific function to call. Now that we're all set, let's proceed to compile our smart contract code. Compilation is an essential step in the smart contract development process. It ensures that our code is error-free and ready for deployment. To do that, let's click on the Solidity Compiler tab, located on the top left side of the IDE. Click on the Compile button in the Remix IDE interface. The compiler then will analyze our code, check for any errors or warnings. You can see that we have a green check mark in our Solidity compiler. It means that our code is free from errors. Once the code is compiled successfully, we can proceed to the next step, deploying and interacting with our smart contract. But before that, let me walk you through on how to change your network to Mumbai Matic Test Network. Let's proceed to the Changes website. The link to this website is provided in the video description. Let's type Mumbai in the search bar. Don't forget to toggle the Include Testnet. From the result, you can see the Mumbai. Click Add to MetaMask. Click Approve and switch network. You can see that we are now in the Mumbai Matic Test Network. To deploy our smart contract, we also need Matic and Link Test token. Go to the Polygon Faucet website, click MetaMask, and copy your wallet address. Paste it and click Submit. Let's click Confirm and wait for our test token. Click this button. And wait for your link token. Now let's go back to the Remix IDE. By the way, if you can't see your link token, just copy this address, click Import, and paste it here. Now let's deploy our smart contract by clicking the diamond-like icon. In the environment field, select the injected provider MetaMask. Click Deploy. Let's confirm our transaction. And we have successfully deployed our smart contract in the Ethereum network. But you can see that we have zero balance of Ether and Link tokens. Let's open our MetaMask and send Ether and Link tokens to our smart contract. First, let's copy our smart contract address. Click Send. Paste it. Let's input 0.1 for now. Click Next and confirm. And we'll do the same thing to the Link token. For the Link token, I'll send 10. Let's check our balance. To test our smart contract, let's place an entry fee. Let's go to the Ethereum unit converter. Let's input 0.01 Ether. And let's copy the way equivalent of our Ether. Going back to the deploy and run transactions interface, let's paste it in the value field. Let us now place our predictions. It could be 0, 1, or 2. 0 for red, 1 for draw, and 2 for blue. Let's click the Start Game button. You will see here that we are transferring 0.01 Ether to the smart contract. Let's confirm our transaction. Now let's check the events. Let's click the green check mark. Here you can see the game ID that was emitted by our smart contract. Let's copy this and paste it in our game status function. Here we can see the results of our prediction. Since my prediction is draw and the result is draw, the smart contract will automatically send rewards to my wallet. We can also check our smart contract balance. You can see that 0.02 was deducted in our smart contract. And that's it for our smart contract. We can now implement it to our front end. For our front end, let's proceed to this repository. Again, links will be provided in the video description. You can download these files, or you can also go to GitHub Sandbox by adding box between hub and .com. To test your own smart contract, let's proceed to the app.js. Go back to the Remix IDE, copy your smart contract address, and paste it in this constant variable. Let me also demonstrate on how our application works in the front end using GitHub pages. You can see our wallet balance here. Let's select 0.1. And my prediction is blue. Let's confirm the transaction and let's wait for the result. There you have it. We have successfully created a boxing-based D-app lottery game with the integration of Chainlink. Thank you so much and happy coding!